Right now, in labs scattered across the world, machines are quietly proving something that was considered impossible just 5 years ago, that the more you scale them up, the more reliable they become. And if that sentence doesn't sound like a big deal to you yet, stick around, because by the end of this video, you'll understand why physicists are calling this the most important threshold in the entire history of computing. For as long as quantum computers have existed, they have carried a strange and frustrating curse. Every other piece of technology humanity has ever built follows a simple rule. The bigger and more complex you make it, generally speaking, the more powerful it becomes, and often the more stable it becomes too. A larger bridge can hold more weight. A bigger engine can produce more horsepower. A larger classical computer chip, packed with more transistors, can process more information faster and more reliably than a smaller one. This is the story of technological progress that we have all grown up with. Bigger, in almost every case, has meant better. Quantum computers broke that rule completely. For over 4 decades, ever since physicist Richard F. Feynman first proposed the idea in 1981 that a computer built from the strange rules of quantum mechanics could simulate nature in ways no classical machine ever could, engineers ran into the same brutal wall again and again. The bigger they built these machines, the worse they behaved. Every additional qubit, the basic unit of quantum information, added into the system, brought with it more noise, more instability, and more opportunities for the fragile quantum states to collapse before they could finish a single useful calculation. It was like trying to build a tower out of soap bubbles. The moment you tried to stack more than a few together, the whole thing dissolved. This is the reason quantum computing spent so many decades trapped in what scientists call the laboratory phase. Not because the theory was wrong. The theory was, and still is, beautiful. Quantum mechanics genuinely does offer computational shortcuts that classical physics simply cannot match. But theory and engineering are two very different beasts, and for 40 years, engineering was losing. To understand why this is so difficult, you have to understand what makes a quantum computer fundamentally different from the laptop or phone you're using right now. Classical computers store information in bits, and each bit is either a 0 or a 1. Simple, stable, unambiguous. A quantum computer instead uses qubits, and a qubit can exist in a superposition of 0 and 1 at the same time. It can also become entangled with other qubits, meaning the state of one qubit is directly tied to the state of another, no matter how far apart they are physically separated. These two properties, superposition and entanglement, are what give quantum computers their extraordinary theoretical power. They allow a quantum machine to explore a staggering number of possible solutions simultaneously, rather than one at a time the way a classical computer must. But here's the catch, and it is a brutal one. Those delicate quantum states are almost unbelievably fragile. The slightest vibration, the tiniest fluctuation in temperature, a stray photon, even electromagnetic interference from a piece of equipment across the room can cause a qubit to lose its quantum properties in a process called decoherence. When that happens, the calculation is ruined. To keep qubits stable long enough to do anything useful, many quantum computers have to be cooled to temperatures colder than deep space, isolated in vacuum chambers, and shielded from nearly every form of environmental noise imaginable. And even with all of that effort, errors still creep in constantly. For decades, this fragility created a devastating trade-off. If you wanted a quantum computer powerful enough to solve a real-world problem, one that would actually outperform a classical supercomputer, you needed a huge number of qubits working together. But the more qubits you added, the more error-prone the entire system became, because you were multiplying the number of fragile components that could fail at any given moment. It was a vicious cycle. Scale up for power, and you scaled up your noise right along with it. This is precisely why, for most of quantum computing's history, the machines that existed were sometimes dismissively called noisy intermediate-scale quantum devices, or NISQ machines for short. They were real, they worked, they could do small experiments, but they were nowhere close to being reliable enough for the kind of transformative applications that had been promised since the 1980s. Scientists always knew there was a theoretical way out of this trap. It's called quantum error correction, and the basic idea has been around since the 1990s. Instead of relying on a single, fragile physical qubit to store one piece of quantum information, you spread that information out across many physical qubits, woven together using a mathematical structure known as an error-correcting code. If a handful of those physical qubits experience an error, the surrounding qubits in the code can detect that something went wrong and correct it, without ever having to directly measure and therefore destroy the fragile quantum state itself. The bundle of physical qubits working together like this is called a logical qubit, and in theory, a logical qubit should be far more stable than any of the individual physical qubits that make it up. Here's where the story gets interesting, and where that so-called major line comes into play. The mathematics of quantum error correction predicted something almost paradoxical decades before anyone could actually demonstrate it in a real machine. It predicted that if you could get the error rate of your individual physical qubits below a certain critical value, known as the threshold, then something remarkable would happen. Adding more physical qubits to your logical qubit would not make things worse, the way it always had in the past. It would make things exponentially better. Below that threshold, scaling up stops being a curse and starts being a superpower. Every additional physical qubit you weave into the code would suppress the overall error rate further and further, following what is called exponential error suppression. Above the threshold, the opposite happens, and adding more qubits just makes your errors pile up faster. The entire future of quantum computing hinged on a single question. Could real hardware actually get below that threshold? And could scientists actually prove that this exponential suppression was real and not just an equation on a chalkboard? For most of the last 30 years, the answer was no. Physical qubits were simply too noisy. Engineers could demonstrate small-scale versions of error correction. They could show flickers of the idea working in miniature, but nobody could conclusively demonstrate the full effect, that scaling up genuinely, measurably, reliably reduced the error rate rather than increasing it. This is the line that scientists are now saying has finally, unambiguously been crossed. In a landmark set of experiments, researchers demonstrated a quantum memory built from a structure called a surface code, one of the most promising and well-studied error-correcting codes in the field. They built two versions of this surface code memory, one using a grid of qubits arranged in a pattern with what is called a distance of 5, and a larger one with a distance of 7. Distance here essentially referring to how many physical qubits are woven together and how much redundancy is built into the code. What they found was extraordinary. As they increased the code distance, moving from the smaller grid to the larger one, the logical error rate dropped by a factor of roughly 2 every single time they scaled up. Not randomly, not occasionally, consistently, and in a way that matched the theoretical predictions almost perfectly. Their largest logical qubit, built from 101 physical qubits working in concert, achieved an error rate of just a fraction of a percent per correction cycle, and critically, this logical qubit outlasted the very best individual physical qubit inside it by well over double. In other words, the whole had become more reliable than any of its individual parts. That had never been convincingly shown before. This is why physicists are using words like historic and turning point, words they tend to use extremely sparingly. Because what was demonstrated here was not just an improvement in performance. It was proof of a fundamentally different relationship between scale and reliability, one that inverts the entire curse that had haunted quantum computing since its inception. For 40 years, bigger meant worse. Now, for the first time, bigger reliably means better, as long as you're operating below that critical threshold. It's worth pausing here to really let that sink in, because the implications ripple out far beyond a single laboratory result. Think back to the history of classical computing for a moment. Before the invention of the transistor in the late 1940s, computers were built from vacuum tubes, enormous, power-hungry, unreliable components that would frequently burn out, generate huge amounts of heat, and had to be manually replaced. Some early computers had rooms full of technicians whose entire job was walking around hunting for the vacuum tube that had just failed and swapping it out. Scaling those machines up was a nightmare, because more components simply meant more failures. The transistor changed everything. It was small, it was reliable, and crucially, as manufacturing techniques improved, you actually could pack more and more of them together without a proportional increase in failure rates. That single shift is what allowed computing to go from room-sized machines that could barely perform basic arithmetic to the supercomputer sitting in your pocket right now. Many physicists now believe that error correction crossing this threshold represents an equivalent transistor moment for quantum computing. Before this, scaling up was fighting against the fundamental physics of the machine. Now, for the first time, scaling up is working with the physics, not against it. Multiple organizations, not just one lab chasing headlines, have now independently pushed into this new territory, using genuinely different physical approaches to build their qubits, which matters enormously for how seriously the scientific community is taking this moment. One major technology company built its breakthrough using superconducting qubits, tiny circuits made from materials that only exhibit quantum behavior when cooled to temperatures colder than the vacuum of outer space. Their processor became one of the most cited examples of this new era of exponential error suppression. And it wasn't operating in isolation. A separate collaboration between another major technology company and a smaller quantum hardware firm demonstrated their own logical qubit system, again independently confirming that the threshold could be crossed using a different set of engineering choices. Meanwhile, an entirely different class of quantum computer, one built not from superconducting circuits, but from individual atoms, suspended and controlled with lasers and what are called optical tweezer arrays, pushed the frontier of scale even further, demonstrating dozens of error-corrected logical qubits at once, more than any superconducting system had achieved at the time. This convergence matters because it tells scientists something crucial. This is not a fluke of one particular material, one particular company's engineering trick, or one lucky experimental setup. Multiple, wildly different physical platforms, superconducting circuits, trapped ions, and neutral atoms among them are all independently confirming the same underlying physics. When that happens in science, when different teams using different tools all converge on the same result, it stops looking like an anomaly and starts looking like a fundamental truth about how the universe works. That consistency across platforms is a big part of why the scientific community has grown so confident that this threshold is real, reproducible, and here to stay. Each of these platforms comes with its own particular strengths and trade-offs, which is part of what makes this moment so fascinating to watch unfold. Superconducting qubits benefit from decades of manufacturing experience borrowed from the broader semiconductor industry, and they can be switched extremely fast, but they demand punishing cryogenic cooling and dense, delicate wiring. Trapped ion systems tend to boast some of the highest gate fidelities in the entire field, meaning each individual quantum operation is unusually clean and precise, though historically their operations have run a bit slower. Neutral atom platforms, held in place by grids of laser light, offer a strange but powerful advantage. The physical layout of the qubits can be reconfigured on the fly, atoms shuffled around mid-computation like pieces on a chessboard, which turns out to be remarkably useful for certain error-correcting codes. No single platform has definitively pulled ahead of the others across every measure that matters, and many researchers now suspect the eventual winner, if there ever is a single winner at all, may borrow ideas and techniques from several of these approaches simultaneously, rather than any one of them sweeping the field entirely on its own. Now, before you get too far ahead of yourself, imagining a world where quantum computers instantly crack every encryption system on the planet or cure every disease overnight. It's important to be honest about exactly what has and has not been proven yet. Crossing the error correction threshold is a necessary condition for building a truly useful, large-scale, fault-tolerant quantum computer. It is not, by itself, sufficient. There is still an enormous amount of engineering standing between where we are today and a machine that can outperform every classical supercomputer on Earth at genuinely useful tasks like simulating new drug molecules, designing next-generation batteries, or optimizing global financial markets. The most careful and measured researchers in the field describe the current moment quite precisely. What has been convincingly demonstrated so far are logical qubits in the range of tens, operating below the critical error threshold, running short quantum circuits that classical computers genuinely struggle to simulate. That is scientifically enormous. It proves the core physics works exactly as predicted, but it is not yet the same as a machine that can run the kind of long, deep, complex computations needed to, for example, break modern encryption standards, or fully simulate the behavior of a complex molecule down to every last electron. Those applications will likely require systems with hundreds or even thousands of logical qubits, each one built from potentially thousands of physical qubits, all working together with error correction happening in real time faster than errors can accumulate. The most realistic projections from researchers working at the cutting edge suggest that the first truly fault-tolerant quantum circuits, ones running dozens of logical qubits with corrections happening reliably below threshold on deep, complex circuits, are still a small handful of years away, likely arriving somewhere in the next 2 to 3 years. Not tomorrow, but also not decades away the way many assumed even just 5 years ago. There's also a second, quieter engineering challenge that doesn't get nearly as much attention as raw qubit counts, but might be just as important. It's the decoding problem. Every time an error-correcting code detects a potential error, some classical computing system sitting alongside the quantum processor has to rapidly figure out what went wrong and instruct the system on how to fix it. And it has to do this incredibly fast, faster than the qubits naturally lose their coherence. If the classical decoder is too slow, errors will simply pile up faster than they can be corrected, no matter how good your underlying quantum hardware is. Remarkably, this is another area where 2026 has seen genuine, measurable progress. Multiple research groups have pushed decoding latencies down into the sub-microsecond range, essentially proving that the classical side of this partnership, the fast traditional computing systems working alongside the quantum processor, can keep up with the pace demanded by the qubits. That might sound like a small technical detail, but it removes what many engineers considered one of the most serious potential bottlenecks standing between today's small-scale demonstrations and tomorrow's large-scale, genuinely useful quantum computers. So what actually happens once these remaining engineering hurdles are cleared? What does a world with mature, fault-tolerant quantum computers actually look like? And why are scientists, investors, and governments pouring billions of dollars into crossing this line as fast as possible? The applications being discussed are not incremental improvements. They represent entirely new categories of computation becoming possible for the very first time. Take drug discovery as one example. Right now, when pharmaceutical companies want to understand how a new drug molecule will interact with a protein in the human body, they rely heavily on approximations, because the actual quantum mechanical behavior of every atom involved is simply too complex for classical computers to simulate exactly, even using the world's most powerful supercomputers. A sufficiently large, error-corrected quantum computer, by contrast, is naturally built from the same quantum rules that govern how atoms and molecules actually behave. It wouldn't be approximating the chemistry. It would essentially be running the chemistry directly, using quantum mechanics to model quantum mechanics. Researchers believe this could dramatically shorten the time it takes to discover new medications, new materials for more efficient solar panels or longer-lasting batteries, and new catalysts for cleaner industrial processes, potentially saving years of trial and error laboratory work that currently defines those industries. Then there's the question of cryptography, which tends to grab more headlines than almost any other application. Much of the encryption protecting your bank details, your private messages, and sensitive government and corporate data today relies on mathematical problems that are extraordinarily difficult for classical computers to solve. Things like factoring extremely large numbers into their prime components. A sufficiently powerful, fault-tolerant quantum computer, running an algorithm developed by mathematician Peter Shor back in 1994, could theoretically solve those same problems in a tiny fraction of the time, potentially rendering much of today's encryption obsolete. This is precisely why governments and corporations around the world have already begun transitioning toward what's called post-quantum cryptography, new encryption standards specifically designed to remain secure even against a future quantum computer. It's a bit like reinforcing a dam before the flood arrives, rather than waiting until the water is already rising. Beyond medicine and cybersecurity, there are applications in climate modeling, where quantum computers could potentially simulate incredibly complex atmospheric and oceanic systems with a level of precision classical machines simply cannot reach. There are applications in financial modeling, where quantum algorithms could optimize massive investment portfolios or assess risk across tangled webs of global markets far more efficiently than today's methods. There are applications in logistics and supply chain optimization, the kind of problems that involve finding the single best solution among an almost incomprehensibly large number of possibilities, exactly the type of task quantum computers are theoretically built to excel at. But it's worth being clear-eyed about the timeline here too, because hype in this field has a long and well-documented history of outrunning reality. Nobody serious in the field is claiming that next year you'll be renting a quantum computer from the cloud to instantly design a miracle drug. What is being claimed, and what the evidence increasingly supports, is that the single biggest scientific obstacle, the one that made many experts skeptical for decades that a truly useful quantum computer could ever be built at all, has now been experimentally overcome. The physics genuinely works. Scaling up genuinely helps, rather than hurts. What remains is not a question of whether this technology is theoretically possible anymore. It's a question of engineering, manufacturing, and time. The same kind of challenge humanity has faced and ultimately solved with nearly every other transformative technology in history, from the printing press to the airplane to the classical computer itself. It's also worth noting that this shift from a physics problem to an engineering problem is exactly the kind of transition that tends to attract massive investment and accelerate progress dramatically. When something is fundamentally uncertain, when nobody knows if the underlying science will even work, it's incredibly risky to pour billions of dollars into scaling it up. But once the core physics has been validated, once you know the path forward genuinely leads somewhere real, investment tends to flood in because now it becomes a race to execute rather than a gamble on unproven theory. That's precisely the pattern we're seeing right now, with major technology companies, government research agencies, and specialized quantum startups all racing to be among the first to build machines with hundreds and eventually thousands of stable logical qubits. There's a hybrid future being discussed as well, one that's worth understanding because it's probably closer to reality than the popular imagination of a single quantum computer replacing every classical computer on Earth. Most experts don't believe quantum computers will ever fully replace the laptop, phone, or server sitting near you right now. Classical computers remain extraordinarily good, fast, and efficient at the overwhelming majority of everyday computing tasks, from browsing the internet to running spreadsheets to streaming video. What's emerging instead is a hybrid model, where quantum processors handle very specific, narrow types of problems, the ones involving massive combinatorial complexity or genuine quantum chemistry, while classical systems continue to handle everything else, feeding data back and forth between the two. In this future, you likely won't own a quantum computer any more than you personally own a massive server farm today. Instead, you'll access quantum processing power through the cloud, The same way you might rent computing power from a cloud provider right now, sending a specific, narrow problem off to be solved by a quantum system somewhere in a specialized facility, then receiving the answer back on your ordinary device. Standing back from all the technical details, what makes this moment genuinely remarkable is not just the specific numbers, the qubit counts, the error rates, the code distances, as impressive as those results are. What makes it remarkable is the story those numbers are telling. For 40 years, one of the most brilliant ideas in the history of physics sat trapped behind an engineering wall that many respected scientists genuinely believed might never be overcome. Some researchers spent entire careers arguing that useful large-scale quantum computers were simply impossible, that the fragility of quantum states was an insurmountable barrier baked into the fundamental laws of nature itself. That skepticism wasn't fringe thinking at all. It came from serious, respected, credentialed physicists making genuinely serious arguments backed by real mathematics. And now, that specific wall, the one separating theoretical promise from physical reality, has a hole punched clean through it, verified not once, but repeatedly, across multiple independent laboratories using entirely different hardware approaches. That is genuinely rare in the history of science and technology. Most breakthroughs are incremental, a small step forward here, a slight improvement there, accumulated gradually over years or decades. What's happening in quantum error correction right now looks different. It looks like the moment where a fundamental barrier didn't just get pushed back a little further, it got dismantled entirely, and the entire trajectory of the field bent in a new direction because of it. We may look back on the surface code experiments happening right now the same way we look back on the invention of the transistor, not as the moment quantum computers became useful in your everyday life. That's still coming. But as the precise moment when everyone stopped asking whether it was possible and started asking only when. So when you hear that scientists believe quantum computers are about to cross a major line, understand exactly what that means. It doesn't mean the science fiction version of instant miracle machines has arrived on your doorstep tomorrow morning. It means something quieter, but in many ways far more profound. It means the single deepest, most fundamental obstacle standing between quantum computing and genuine world-changing usefulness has just been proven, experimentally, repeatedly, and independently, to be surmountable. The wall that stood for 40 years finally has a door in it, and scientists across the world are walking through it right now, one carefully engineered logical qubit at a time. We are watching, in real time, the earliest chapters of what may end up being one of the most important technological stories of the century. The kind of story that decades from now people will trace back to this exact moment, this exact threshold, this precise line that so many believed could never truly be crossed. And now, according to the scientists who have spent their entire careers chasing it, it finally has been.